chapter is over. Next we have Fanno flow. So Fanno flow also more or less similar, but the changes happen due to the friction. Okay, so we will add the viscous force also in the calculation. So in the relay flow, there is a heat transfer, and here it happened due to the viscous. So here we don't consider the heat transfer. Okay, so heat transfer will not be considered. We know even due to the viscous there will be a small heat generation, but we assume there is no heat generation here. Okay, so here due to the viscous dissipation only P naught is reduced, T naught is constant, like normal shock, oblique shock, etc. Okay, here also it will be subsonic flow will be accelerated maximum to 1, supersonic flow will be decelerated to maximum 1. So here also we are taking one long duct. Okay, and there is a frictional effect, so viscous force also we should consider. So same continuity, and energy equation we don't take the Q value because there is no heat addition or rejection. So the simple isentropic, and that is without Q value, without heat transfer we are taking it. Then this momentum equation, these two are same. Additionally we are adding this friction component, frictional force. Okay, and if this is the flow direction, then the frictional force will act in the opposite direction. Okay, because the friction force will resist the flow, so it will be in the opposite direction. So the bottom one is the flow direction, opposite you will have the frictional force, so I am taking as minus Fv. Okay, so these three are the basic equations: continuity, momentum, energy. Here there is no Q term, and here we have added the frictional component. And assume I am taking the circular duct, circular pipe. So area everywhere is pi d squared by 4. Okay, A1, A2, etc. and all pi d squared by 4, which is constant. Then we will come to that frictional force Fe. I can write this Fe in terms of shear stress, also like a normal other lift drag forces. So how you will write the force? It can be in terms of pressure into area. Okay. Similarly, here it is shear stress into area. Okay. So that frictional force, if you take, it is acting inside the circular faces, right? Everywhere inside the circular face, it will taken, it will be acting. So my area will be the pi dl. Okay, I cannot take this cross-sectional area because frictional force act inside the circular tube area. So my area is pi dl, and this is shear stress. So this is one way I can write it, or another way like half rho v squared SCL. How we will write the lift? Same way also we can write it. So half rho u square, and here the force acting on this circumference, so it is pi dl. Then instead of CL, here I am taking F. Okay, frictional coefficient. So CL is lift coefficient. Similarly, even I can mention CF also, but simply they have mentioned the F. So friction coefficient. In two way I can write it, but this one I am going to use it for the further derivation. Is that clear? So now this component I'm going to substitute here. Okay, so same equation. So first what I'm doing, I'm dividing this equation by A. Okay, so A1 is equal to A2 is equal to A. First divide this equation by A. So I will get P plus rho U square minus Fe by A is equal to P2 plus rho 2 U2 square. Taking this term here, so that I'm getting P2 minus P1 plus rho 2 U2 square minus rho 1 U1 square. Then this side I'm having only minus Fe by A. So instead of A, I will substitute pi d squared by 4. Then instead of this Fe, I am substituting half rho U squared pi dl F. That's it. So this equation, these two I am taking to the right hand side. Okay, these two terms, and on the left hand side I'm substituting a value, also the fe value, so I'm getting this equation. This also further if you simplify pi d etc and all, this will be my final equation. This, so they are taking one small shaded region, so they are writing this equation for that shaded region first, then they are integrating for the complete length from 0 to L. Okay, so the same equation, assume I'm taking on small distance dx, so they are writing this equation for the small shaded region, then if you integrate you can find it for the long duct, like that they are proceeding. So previously I got P2 minus P1 plus rho 2 U2 square minus rho 1 U1 square minus 4 of L by D of rho U square. This is what you derived in the last slide. Now if you apply this equation to the small shared region dx, instead of this L I should substitute dx, right? Because I am taking only the
Yes,
small
sir.
distance dx. Then if I integrate it from 0 to L, I can get it for the complete depth. That's what they have mentioned. This equation. So same equation in the integral form they have written. Right formula. Now we are taking only the shaded region. Okay, so simply I'm taking dp. This is so d rho u square, and here there is no integral, only 4 of dx by d. Okay, this is for the complete duct. Okay, integral term. Now I'm taking only for the shaded region. Now I'm going to simplify this equation further. Later I can integrate it for the complete duct. Okay, so this is only for the shaded region, and here you see so dp plus d rho u square. So this they are going to differentiate. So uv formula only. Okay, this differentiation of uv, you will get these two terms, that is u dv plus v du, like that we are writing it. So this is fine, but here if you see, just now we write the continuity equation. Rho 1 u1 is equal to rho 2 u2 is equal to constant. Okay, so using that, if you take this is constant and differentiation of this constant is 0, so this term will be 0. Is that clear?
Yes, sir.
So instead of d of rho u square, I can take only rho u du. Okay, so dp instead of this, simply it is rho u du, and this time same thing they are taking. Okay, so leave this now. So instead of this, we found it is rho u du, rho u du. Simply substitute. We got this equation. Then they are taking this half rho u square to the left hand side, so that I am getting 4 of dx by d is equal to 2 dp by rho u square minus rho u du by rho u square. This also I can further simplify. Rho get cancelled, u get cancelled. So remaining what I will get it, minus 2 dp divided by rho u square minus du by u, I will get it. Is that clear?
Yes, sir.
Then they are converting this term further in terms of Mach number. So for that they are using this. So already we studied in the diamond aerofoil, we can convert rho u square in terms as a gamma p m square. So instead of this rho u square, they are substituting gamma p m square. Okay, so instead of this they are writing gamma p m square. Then this time itself they are rewriting as minus 2 divided by gamma m square dp by b minus, oh, 1 2 is there here, sorry, minus 2 du by u. Okay, here I missed the 2, sorry. So like that they are writing the 4 of dx d equation for the shaded region. Is that clear?
Yes, sir.
And then they are converting this dp by p in terms of Mach number, again du by u in terms of Mach number. So now substitute. So in this equation, substitute instead of dp this one, instead of du this one, you will get this equation. Is it clear?
Yes, sir.
That's it. This is for the shaded region. And if you want it for the complete duct, simply you will integrate it. So the length varies from 0 to L and Mach number varies from M1 to M2. Okay, here we have M1, length distance are start from 0 and L. So here I have M2. So length from 0 to L, Mach number from M1 to M2. Now you integrate and apply the limit. What will happen? So here I will get simply 4 of L by D, right? I will get 4 of L by D minus 4 of 0 by D. So it is simply 4 of L by D. And here after integrating, I am getting this term. Simply you have to apply the limit. So finally I am getting 4 of L by D whole term in terms of M2 minus whole term in terms of M1. That's it. And remaining properties, it is very easy only. See here the flow is adiabatic. There is no heat addition or rejection. So T naught is constant. Assume this is the duct. So due to the friction, so only this P naught 2 is reduced. Okay, there is a stagnation pressure loss, but there is no heat addition. So T naught 1 is equal to T naught 2. So here we have to find the relation between T2 by T1. So simply in this station, I can find T naught 1 by T1. Then here using isentropic relation, I can find T naught 2 by T2. Then using the 2 ratio, I can find the first relation, T2 by T1. Then for the P2 by P1, simply I can use P is equal to rho or T relation. Okay, so R is cancelled, so you will get only rho and T term. Then this rho term I can convert in terms of velocity using continuity equation. Okay, rho 2 by rho 1 is equal to U1 by U2. Then this U I can convert it into Mach number into speed of sound. Then that A I can write it into that is root of gamma RT, gamma R are constants. So remaining you will get only root T terms. So now I have Mach number. Again, both temperature I know in terms of Mach number. Finally, I can get in terms of Mach number, P2 by P1. Same way, rho 2 by rho 1. Okay, we know P2 by P1, T2 by T1, substitute, you will get that. Then P02 by P01, which is not constant. So here it is similar to the Rayleigh flow. So in the station 1, I am going to find P01 by P1 using isentropic relation. Then the station 2 also using isentropic relation, I am going to find P02 by P2. Then already I found P2 by P1. Using these three, I am going to find P02 by P01. Then here also, we don't know how the inlet flow, it can be subsonic or supersonic, will be affected due to the friction. So that they are checking using two problems. First problem they are taking subsonic Mach number, second problem they are taking supersonic Mach number. But this flow phenomena, it is almost similar to the Rayleigh flow. Here also, both subsonic, supersonic, maximum can be accelerated to 1. Accelerated or decelerated to 1. Okay, subsonic will be accelerated, supersonic will be decelerated. Here also, if you further increase, there will be a pressure propagation wave for the subsonic, or there will be a normal shock wave inside the supersonic. It's almost same behavior. Okay. So here they have taken Mach number 0.3, and due to the length of 30 meter, the 0.3 is converted into 0.475. So if I further increase the length to 50 meter, then this 0.475 may be accelerated to 1. Okay, And if I further increase the length another 30 meter, this side will not vary, it will be fixed. Only this will be reduced to maybe 0.2, almost similar fashion. Is it clear?
Yes, sir.
So there we keep on adding q. Here we are keep on adding the length. Okay, by adding the length, we are increasing the friction. 1 minute. So Mach number 3 is decelerated to 1.9 due to the friction. Okay, and if I further increase the length, maybe here they have taken 5 feet. Another one I 5 feet, if I take, it may be further reduced to 1. If I further increase another one 5 feet, then this side it is choke, this side also it is fixed, and there will be a normal shock which will be moving towards the inlet. Here also almost the same procedure. Okay. So overall, whether it is subsonic or supersonic, maximum it can reach 1. So subsonic means accelerated, supersonic means decelerated, similar to relay. Okay, accelerated, decelerated. Here also there is a stagnation pressure loss due to the viscous dissipation, okay, frictional dissipation. And subsonic, there is acceleration, so Mach number increases, then pressure temperature will decrease. So in supersonic, Mach number decreases, so pressure temperature increases. Okay. And this is the table. So if you know Mach number, you can find, for example, if you know M1, you can find P1 by P star, rho 1 by rho star, T1 by T star, P0 1 by P0 star, and T0 is constant, so that term will not be there. And 4 of L max by D. Okay, so instead of L max, we will use L star. Okay, I will explain. And this is impulse function. It will be used in propulsion, not in our aerodynamics. Okay, this table we are going to use. Again, what we derived is P2 by P1, T2 by T1, rho 2 by rho 1, P0 2 by P0 1 only we derived. But here everything they related static and sonic. So we will see how to convert the static equation to static and sonic. So for example, I will take the first problem. So they are given Mach number 0.3. It is accelerated to 0.745 for the 30-meter length. Okay, this is the original duct. Now imagine I am just extending this duct imaginarily. I am adding another 120 meter so that I can convert this 0.475 to 1. Okay, now this 0.475 will reach sonic if I add this 20 m. Assume this is m1, this is m2. So if you want to convert this m2 to the sonic, then I need 20 meter, so that I can denote it as L2 star. Okay, that is instead of L max, we used to mention L star. This is L2 star. Or if I want to convert this Mach number 0.3 to 1, then I need this L plus L2 star. So that I have given name as L1 star, which is 30 plus 20. Okay. So if you know the M1, using the table you can find L1 star. If you know L2, M2, you can find the L2 star. So L star means L maximum. I can take any arbitrary station that can be converted into sonic by adding the required length of the duct. Okay. So any station can be related to the sonic. So my final control volume will be this one. So any arbitrary stations with a static property, pressure, Mach number, temperature, density, P02, P01, T01, etc. Then this side it can be related to sonic, P star, T star, rho star, P0 star, etc. Okay, so again here also it is similar to the relay flow. So instead of P2, I will T2 I will substitute T. So instead of T1 I will substitute T star. Okay, and M1 is 1, M2 is simply M. So that I am getting T by T star is equal to. So similarly all the parameter, yeah, thank you. All the parameter I can convert in terms of static and sonic. Okay, we need this equation to solve the problem. So they will give originally this duct only. Okay, so if I want to convert Mach number zero point 0.3 to Mach number 1, I need this L1 star, which is equal to original length L plus imaginary length L2 star. Okay, so L1 star is equal to L plus L2 star. This equation is must. Is it clear?
Yes, sir.
So this, if you rearrange, I will get L is equal to L1 star minus L2 star. And in this equation, if I multiply 4f by d on both sides, I will get this equation. So this only we will use it to solve the problem. Okay. So mostly they will give M1, P1, T1, and what is the length, and what is the dia, and what is the friction coefficient F. So these parameter they will give it. So once you know the M1, your first step should be referring the isentropic table and find these two ratio. As you know M1, P1, you can find T01, P01. Okay. Then second step, for the same M1, now you should go to the Fanno table. Using that you can find all these static sonic relations. P1 by P star, P01 by P0 star, T1 by T star, 4 of L1 star by D. So we know P1, P01, T1, T01, everything. So using that I can find all these sonic properties. Okay, we can find this 4 of L1 star by D. Also all the sonic property we can find it. This is the second step. Then third step, we have to use this formula 4 of L by D. See, already I found 4 of L1 star by D, and this 4 of L by D, they have given what is friction coefficient, what is length of the duct, what is diameter of the duct. Simply substitute. This time also I can find it. Then from this equation I can find 4 of L2 star by D. Right?
Yes, sir.
So once you know this 4 of L2 star by D, again you can go to Fanno table. So this value you can find remaining Mach number, pressure, temperature, P0 ratios, etc. So we know all the sonic properties. Substitute, you will get both static and stagnation. So this is the first problem. See, they are given actually same problem. 0.3 is converted into 0.475. So they are given P1, T1, friction coefficient, duct dia and length. We have to find the downstream property. So first step is referring the isentropic table. You can find P01 by P1, T01 by T1 also. So T1, P1 is known. You can find P01, T01. Then second step, for the same Mach number, Fanno table, you can find pressure, temperature, P01 by P0 star, also 4 of L1 star. So once you know P1, T1, P01, etc., and all, you can find all the star properties. Then third step, using this formula. Okay, so I know 4 of L1 star by D. Also, I know the value of FLD, so that I can find 4 of L2 star by D. So once I know this value, again go to the same Fanno table. You can find corresponding Mach number and other pressure temperature ratios. Substitute all these sonic properties, you can find static stagnation. So in the Rayleigh curve, so that is also drawn between enthalpy and entropy. So this is a static curve which is a little bit inclined upward. Then this is the stagnation curve. Okay, this is the static curve. So here also the upper one is subsonic, it will go to sonic. Then this one is supersonic. Okay, so this is H naught curve. This is what we discussed. Here also almost same, but the stagnation is totally different because here there is no heat addition or heat rejection. So H naught is constant, so we will get a straight line. Okay, so in the Rayleigh flow it is different. Here it is a straight line. That is a major difference. Then on the sonic, that is a static enthalpy curve, if you see, it is little bit raised. Here it is just flat. That's the only difference. Other things are everything is same. Above it is subsonic, it will go to sonic if you keep on increasing the length. Okay, so here the changes happen due to the heating. Here the changes happen due to the increase in length. Okay, so if you keep on increase the length, maybe from zero point 0.3 to zero point 0.5, further it will reach 1. If you further increase the length, which is greater than L max, then this 0.3 will be moving towards to zero point 0.2. Okay, then supersonic also maybe 3. If you keep on increase the length, it will go to 2. Finally, it will reach 1. If we further increase the length, there will be a normal shock wave that will be subsonic and again sonic. So in this problem, so they have given the length 5 feet and dia and friction coefficient also given. Additionally, they are given M1, P1, T1. So what you have to find is the required duct length to choke the flow. Okay, so Mach number is 3, dia F length also given, but they are asking length to choke the flow. That means so this may be L. What they are asking, how to denote that choked length?
L max.
L max, that is L1 max. Right?
Yes, sir.
Because we have to choke this M1. We have to convert this M1 to 1. So L1 max, that we used to denote as L1 star. Okay, here how to find it? Of L1 star by D. Now from this ratio, I know the F value, I know the D value, 4 also it is given. From that I can find L1 star. So if you find that L1 star, it will be 10.44 feet. Okay. So initially they are given length of 5 feet with Mach number 3. That means this 5 feet is maybe decelerating this Mach number 3 to 2 or something else. Okay. So if you want to achieve sonic at the end, then we should further increase the duct to, I think, 5.44 feet. Is that clear, this problem?
Yes, sir.
Okay. These are all just four problems only, mainly. And in the second problem, here also for the duct, they have mentioned M1 value 1.8, M2 value 1.2, then P1 is given. So you have to find P2 4 of L by D. Here, what is the procedure? These two you have to find it.
So from M1 we'll get 4 of 4 FL 1 star D divided by D, and from M2 we can get 4 FL L star 2 divided by D, and from that we can find 4 FL by D.
Okay, very good. Plus or minus, right? So
Yes, sir,
these,
minus.
yeah, these two value we know. Substitute, you will get this value. Okay, this is correct. Then this P2, P1 is 40 psi. P2 you have to find it.
So we can find the P by P star ratio for M1 and then find P star from that.
Okay, for the using the Fanno flow for M1, I can find P1 by P star. Then
So then we can find P star from that and
okay,
use that in
P1
the equation
is
for M2.
okay. We can find P star. Then using the M2, using the Fanno table, you can find P2 by P star. Substitute P star, you will get P2. Okay, so they found P1 by P star, P2 by P star. Also these two ratio. Okay, from these two ratio, okay, they found P2. Then from here they found 4 of L by D. Okay, 0.208. Next problem. So here they have given M2, that is 0.94. M1 is unknown. T1 is given. T2 is given. So you have to find P2 by P1. So these two value you have to find it here. Okay. So you can find maybe P2 by P star, P2 by T star, P02 by P0 star, then 4 of L2 star by D, right? Even row 2 by row star, everything you can find it. Okay, next step.
So then you can find T star using T2.
Okay, from that you can find T star, then
So then you can find the ratio between T1 and T star and associate the Mach number.
okay, we can find T1 by T star. Then you can go to again same Fanno table. You can find the M1 P1 by P star, P01 by P0 star, 4 of L1 star BD, like that. Everything you can find it. Okay, this is fine. M1 we found it. Next step.
So then
P2 by P1.
so we can use both ratios P1 by P star and P2 by P star to find P1 by P2.
Okay, so P star is common. Any station can be related to sonic. So you can take the ratio from there you can find P2 by P1. Okay, very good. So for M2, using Fanno table, they are finding the temperature ratio from the T star. Then they are finding T1 by T star. From there they are finding M1. Then for both M1 and M2, they are finding P by P star from the Fanno table. From there they are finding P2 by P1. Okay.